Hello everybody, and welcome to the second module in this introductory series on FMCW radars. In the previous module, we analyzed the frequency of the IF signal and showed that this frequency was directly proportional to the distance of an object from the radar. In this module, we will look into the phase of the IF signal. Studying the phase is very important if we wish to understand the capability of an FMCW radar to respond to very small displacements in objects. This is what enables the radar to very quickly and accurately measure the velocity of objects. This is also the foundation for the use of radar in applications such as heartbeat monitoring and vibration detection. We are going to start this module with a very quick overview of some relevant concepts in Fourier transforms. A sinusoid in the time domain produces a peak in the frequency domain, the location of the peak corresponding to the frequency of the sinusoid. It is important to understand that the signal in the frequency domain is a complex number with an amplitude and a phase. So while this plot here represents the amplitude of the Fourier transform, each of the values here is in fact a complex number with an amplitude and a phase. Recall that a complex number can be mathematically represented in the form a e power j theta, where a is the amplitude and theta is the phase. Alternatively, it can also be pictorially represented as a phasor, which is a vector with the length corresponding to the amplitude a and a direction corresponding to the phase theta. Throughout the series, we will stick with this phasor representation since I think it has a more intuitive feel to it. An important property of the Fourier transform is that the phase of the peak corresponds to the initial phase of the sinusoid. So this sine wave over here starts with a certain initial phase, and that phase is reflected in the phase of this peak here in the Fourier transform. This here is a sine wave which has the same frequency as the sine wave above, but has a starting phase which is 90-degree offset from this phase. So correspondingly, the Fourier transform will have a peak which is at the same location as this, but with a phase that is offset by 90 degrees compared to this previous peak. One thing that I should point out here for the sake of completeness is that the properties I have just described are strictly true only for a complex input tone, that is an input tone of the form e power j omega t. However, conceptually these ideas are equally applicable to real input signal such as these sine waves over here, barring a few mathematical modifications that I have conveniently decided to gloss over because I think it distracts from the core concepts that we are trying to get through here. Let us quickly recap some material from Module 1. We saw that an FMCW radar transmits a signal called a chirp, which can be represented using a frequency versus time or FT plot as shown here, or equivalently using an amplitude versus time or AT plot. Focusing on the FT plot, we saw in Module 1 that the radar receives a reflected chirp from an object after a round-trip delay of tau. The transmit signal and the reflected signal are mixed in a mixer to create an IF signal which has a constant frequency of s tau or equivalently s2d by c, where d is the distance of the object to the radar. So in Module 1, we use the FT plot to analyze the relationship between the frequency of the IF signal and the distance to the object. In this module, we are going to use the AT plot to analyze the relationship between the phase of the IF signal and the distance to the object. So the top figure here shows the AT plot for the TX chirp. The one in the middle is the RX chirp, which is just a delayed version of the TX chirp, delayed by an amount tau, tau being the round-trip delay. And as we learned earlier, for a single object, the IF signal is going to be a constant frequency signal. In other words, a single sinusoid. So mathematically, I can represent this IF signal as A sine 2 pi ft plus phi naught, where f, the frequency, is given by s 2d by c, s being the slope, d being the distance to the object, and c the speed of light. And the phase phi naught is just the phase of this IF signal at this point c. Recall from module 1 that the initial phase of the IF signal at the mixer output is the difference of the initial phases of the two inputs. So this phase at C, which is again the same as phi naught, is going to be the difference of this phase of the phase of the TX chirp at point A and the phase of the RX chirp at point B. Now what happens if the phase of the what happens to the phase of the IF signal if the object moves by a small amount such that the round trip delay tau changes by delta tau? The new RX signal, represented by the blue curve here, is going to shift by an amount delta tau. Also, the IF signal is correspondingly going to change. Now the starting phase of the new IF signal, that is the phase of the IF signal at point F, is going to be the difference of the phase at D and the phase at E. Now the phase of the RX chirp at E is going to be same as the phase of the earlier RX signal at B, but the phase of the TX chirp at D is going to be the earlier phase at A with an additional phase offset of 2 pi fc delta tau. And this is because the TX chirp would have traversed an additional phase of 2 pi fc delta tau during this period delta tau. And this additional phase, which is the phase difference between the point A and D, is going to get directly reflected in the phase of the IF signal, that is the phase at F. So this phase, the change in phase of the IF signal as the object, when the object moves by delta tau, is given by delta phi equals 2 pi fc delta tau, which I can also rewrite in terms of the corresponding change in the distance to the object delta d as 4 pi delta d by lambda, where I have used the fact that delta tau is equal to twice the change in the distance divided by the speed of light, and the wavelength is equal to the speed of light divided by the frequency fc. So now, to update our understanding of the IF signal thus far, for a single object in front of the radar, the IF signal is a tone with a frequency that is proportional to the distance of the object and also has a starting phase which has the property that it changes linearly with small changes delta d in the distance of the object. So this is the formula that we now know. For an object at a distance d from the radar, the IF signal is a sinusoid with a frequency f given by this equation here, and a phase which linearly responds to small changes delta d in the distance to the object. We now want to understand how this IF signal changes in both frequency and phase if there is a small change in the position of the object. And by small, I mean small compared to the range resolution of the radar. So it would have to be in the order of millimeters, and let's say 1 millimeter in this example. So consider the chirp shown here. So it is a chirp which has a slope of 50 megahertz per microsecond and has a time duration of 40 microseconds. What happens if an object in front of this radar changes its position by 1 millimeter? And note that for 77 gigahertz radar, 1 millimeter actually corresponds to 1/4 the wavelength. So first, what happens to the phase of the IF signal if the object changes its position by 1 millimeter? So, directly using this formula over here and plugging in delta d equal to 1 millimeter, which is lambda by 4, I get that the change in phase is 180 degrees. Now, what happens to the frequency? So the frequency of the IF signal changes by delta f equals S2 delta d by c, which is directly got from here. And plugging in the values, S is 50 megahertz per microsecond times the distance d is 1 millimeter divided by the speed of light. I get an answer of 333 Hertz. Now, this may look like a big number, but in the observation window of Tc equal to 40 microseconds, this corresponds to a mere 0.013 cycles. So this change would not be discernible in the frequency spectrum. So the takeaway here is that the phase of the IF signal is very sensitive to small changes in the object range. Not so with the frequency, which as we saw is quite insensitive to such small changes. So this slide just reinforces what we learned in the last slide. An object at a certain distance produces an IF signal with a certain frequency and phase. So here you have the IF signal corresponding to a single object. It is a sine wave with a certain frequency and a certain starting phase, 0 in this example. And the Fourier transform produces a single peak, and the phase of that peak is corresponds to the starting phase of this sine wave. Now what happens if we move the object by a small amount? That changes the starting phase, and as you can see here, the phase here has changed by 180 degrees in this example because I'm assuming a motion of 1 millimeter. And correspondingly, the peak of the FFT, the location remains the same, but the phase of the peak has changed by 180 degrees. So it's 0 here and 180 degrees here. So I think we now have all the tools to understand how an FMCW radar can measure velocity. The basic idea is the following. You transmit two chirps separated by a time of Tc. The range FFTs corresponding to each of these chirps will have peaks in the same location but with differing phase. The measured phase difference omega between the phases of these two peaks will directly correspond to the motion of the object. And note that if the velocity of the object is v, the object would have moved a distance vtc during this time period tc. So this is the equation here where the phase difference between the phases of the peaks corresponding to these two transmitted chirps is given by 4 pi times the distance that the object has moved during that period divided by lambda. And then rearranging this equation, you can directly estimate the velocity from this measured phase difference. So the takeaway here is that the phase difference measured across two consecutive chirps can be used to estimate the velocity of the object. Besides velocity measurement, the fact that the phase of the IF signal is very sensitive to small movements is also the basis for interesting applications such as vibration monitoring of motors, heartbeat monitoring, etc. And this slide is a quick introduction to how some of that works. This figure here depicts the time evolution of an object moving with an oscillatory motion. So the object starts at this location, deviates a little bit to the left, comes back, deviates a little bit to the right, and so on. This could represent, for example, a vibrating object. The assumption here is that these movements are very small, so that the maximum displacement delta d of the object is a fraction of a wavelength, for example, a millimeter or less. Now what happens if we place a radar in front of this oscillating object and transmit a bunch of equispaced chirps? Each of these TX chirps would result in a reflected chirp, due to the reflection from this object, and the processed IF signal would result in a peak in the range FFT. Now the frequency of this peak is not going to change much across chirps because delta D is very small, but the phase of the peak is going to respond to the oscillatory movement of the object. And that is what is shown here. So the phase starts off at a certain value and mirrors the movement of the object to the left. And as the object comes back, the phase comes back to its initial value and then deviates to the on the other side. If we plotted this measured phase of the peak across time, in this phase versus time plot, the plot would look something like this here, and you can learn a lot by looking at this plot. So the maximum phase deviation delta phi is related to the maximum displacement delta d, as follows here. And so right here I can estimate the amplitude delta d of the vibration. Similarly, the periodicity of the plot directly gives me the period of vibration. So the takeaway here is that the time evolution of the phase of the range FFT peak can be used to estimate both the amplitude and the periodicity of vibration. This concludes the current module. We learned that the phase of the IF signal is very sensitive to small changes in the range of the object. And we got some sense of how this could be used in velocity estimation. We now have the necessary background to begin answering the question that we had asked at the end of module 1. So we have multiple objects which have different velocities relative to the radar. However, at the time of measurement, these objects happen to be virtually equidistant from the radar. So the range FFT is obviously going to show you only a single peak corresponding to this range T. How do we now separate such objects? It turns out that equirange objects which have differing velocities relative to the radar can be separated out using what is known as a Doppler FFT. And this is something we will look at in the next module.